Hi everybody, welcome back to a continuation of the Willem programmer for EPROMs. Before I get into it, I'd like to make an apology for some errors in the previous video. I had this EPROM chip sitting in the topmost position, which I'd got from researching blogs in the AI from Google. But this makes it quite clear that it should be sitting right down, as far down as it can sit. And you can't see it, but the actual orientation notch is up at the top there. I'm going to spend some time going over this circuit diagram, a really nice circuit diagram that I found on the UK Vintage Radio site. We'll start going through just exactly how the power supply works. So here you can see a USB input, and here is, I don't know, he seems to have cobbled up a diode or something, but it's basically the socket for the other type of power supply. And over here, it puts out via this 7805 regulator, the regulated voltage here, which will be, let's just say to start with, 5 volts. If I was to use the USB, it just taps straight in here to the 5 volts. And so basically from there, doesn't matter whether you have the USB or a 12 volt voltage power supply in the jack plug, you will only get, let's say, around 5 volts, and I'll discuss that a bit more at this point here. So how do you get the programming voltages? Well, this thing here in this circuit is a buck boost circuit, and this is the oscillator and so on and so forth, and inductor and so on. Here are some jumpers you can swap. So VPP, the programming voltage, can be selectable with these from a series of voltages from 12.5 up to 25. And I've checked that it does produce those, and I'll maybe demonstrate that later in this video. So you can see from this diagram, it's actually for a PCB 5.0. As best I can find out, they started making these at about 2007, and the 5 or 5A became fairly ubiquitous around about 2010, 2012. There also seems to be a B version around. The version I have is the version T, which seems to crop up quite a bit later, maybe to 2020. And it doesn't really follow this, as there's some exceptions, but this is a pretty good starting point for the discussion. So let's start looking at this circuit here. Now, there's quite a history of power supplies and so on up to about 2000. They were all over the place. And the 12 volt power supply that people might be talking about for this, in fact, was AC. So you can see that there is a diode bridge here to rectify it. And it goes into a 7805 regulator. Now that will put 5 volts here on Vreg, and that's it. However, if you have a little bit of head height on that 5 volts, you can trick this thing to give a little bit more. And if you look at how this is wired here, you'll see that at the moment, this jumper actually short circuits this floating ground down to the earth rail. So you get 5 volts. And so that jumper you'll see later on. You can put it on this other pin here, and it means that this ground actually goes through this diode, and as I measured on my one, it gives you exactly 0.6 of a volt forward bias on that diode, so you get 5.6 volts here, which it seems to be required for some chips. I don't know what. What they don't mention is if you pull it off completely, it'll go through both diodes, well, you don't mention it on the silk screen, shall we say, you'll get 1.2 extra voltage here, and it'll put out 6.2 volts here. So there's a slight exception. The thing is that actually on my one, this is a 78M05. And unlike its bigger brother, it can only put out half an amp. And I found, in my case, in addition, the bridge is missing. It just has this forward bias diode here. And in fact, I've seen some boards that have a jumper, a header and jumper there instead. And it turns out on mine, if I put 7.5 volts in here, I can get just under the 5.6 volts. If I want to do 6.2 and 5.6, I need to put 9 volts on here. And the reason I say this is that this regulator is sitting on a separate patch of what would otherwise be the earth plane for the main board. So that patch becomes its own heatsink. Now, I've seen some of the build-yourself kits where they actually do have an aluminium heatsink on this, but this is my one's a surface mount. And it sits right on the little bit of copper there, and it doesn't have much heat dissipation. And I think if you put a 12-volt supply on here, you're going to be dropping at least 6 volts in this at possibly half an amp, and this will get hot. So it may be that a 12-volt power supply puts you in jeopardy because this has an internal overheat circuit. And if you're programming and it needs that half an amp, and it's got to drop half an amp at 6 volts, this may get hot enough to start thermally shutting down, and halfway through blowing the chip, the 12-volt thing will actually start, the current to the VPP here will start fading, and it will drop its voltage. So my suggestion, if you are going to use an extra supply because you need that 5.6 volts, don't put a high voltage supply here, maybe 9 volts. The higher voltage might get you in trouble. Now, around the time that this Series 5 started, let's say 2010, 2012, we're in the territory of USB 2, and odd as it might seem, USB 2 is capable of half an amp. So if you look at the USB, it comes straight in here to exactly the same VReg point. So basically, no matter whether you use this power supply on here or a USB 2 or 3, you're only going to get 5 volts here. What's more common is almost everybody has a tablet or a mobile phone, and almost all of them will come with a recharging pack, which is 5 volts. My little tablet actually can do 1.5 amps. So most people will have, kicking around at home, a perfect thing to plug into this USB, and the board comes with a cable to plug straight in to my USB charger. So I would say for most people, it's fine using either your computer's USB 2. USB 3 is even better. It puts out about 0.9 of an amp. So either that or your slightly more powerful phone charger. And that's it. I think that's your power supply. So now let's look at my actual circuit. You can see I put it in a little plastic box I milled up. Okay, so let's start with the 5-volt circuit. Here is the external jack plug, and you can see its center lead here, and you can see the track coming to that single diode, which is mine uses instead of the full bridge rectifier. From here it goes to the leg of this tank capacitor here, and then around to this leg here on the 78M05 regulator. You can also see here the isolated patch, which is isolated from this rest of this earth plane on the board. And this is the jumper that I was talking about for the supply sitting on the 5-volt position. And here it shows you on the cell screen the 5.6. But be aware, if you are using this USB as the input, putting it on the jumper on 5.6 volts will not get you 5.6. It'll stay at 5 volts. You can't create voltage out of nothing with just a plain regulator. Next we have here, this is the buck boost area here. This is the chip controlling the buck boost. This is an inductor. I know it looks like an electrolytic, but it's actually a bobbin inductor with a little bit of heat shrink on it, so it's masquerading. This is the tank capacitor for the buck boost. And here, this VPP does not, in my case, relate to this diode. I'll get back to that. It's actually about this lookup table here. And you can see that this lookup table tells you the position to put this jumper and this jumper. So you can see 6 and 7 here. In the position it's in now, it's 12.5 volts. And you can see you can swap them to get 15, 21, and 25. And I've tried them all, and it definitely, under no load, gives you that. Now, the difference from my one and several others I've seen, VPP is not hooked up to the rail, as I'll go back and show you on the circuit diagram. It's actually hooked up to this impedance matching LED driver. So it's driven, pin 2 goes directly and drives this. And the other leg goes over here to the strobe pin on the parallel port. So when you start up, this is a bit vague about what it does, but as soon as you start running it, the strobe gets this LED, switches off or on depending on whether you're programming or not. I have seen variations on this board where down here, these two diodes are down here nearer the parallel port, which kind of makes sense. Okay, so let's just flip back to the circuit diagram, and you can see here on this circuit diagram, the red LED is actually on VPP. So it's, again, this is a pretty good diagram, but it's not, it doesn't follow this little bit here. Oh, and by the way, these two diodes here, this and this, are those 2.6 volt diodes that this jumper controls to lift the ground plane of this regulator. And for a little bit more, on my board, there's a wire comes through here as a test point for VPP, which is kind of nice. And down here, there's another test pad for the 5 volts coming from the regulator or from the USB. By the way, when you're using the USB input, all of this part of the circuit's bypassed. My board came with a nice little ribbon cable that goes on this header, which is, I think, quite handy. But unfortunately, for some reason, VPP doesn't seem to work. Might be some legacy stuff there. The ground does, but it's a bit awkward to get to. In fact, what I do is, as you've seen, or what you're about to see, I put the test probe in this wire here. It's kind of easy to get to. And then I use these 2 points for the testing of settings on this and so on. Here we are with the jack plug power supply. It's on a 9 volt DC supply. So let's just do some investigations here. We'll put this pin here and we'll check here, and you can see that we're getting the 9.3 volts from the supply. Here we're getting about 0.8 of a volt voltage drop, and if I test on this 5 volt test point, you can see I get 5.03. I've got this jumper here in the 5 volt position. If I take it off, I should get about 6.2. So we'll try that. And there we go. So that's dropping through those two diodes there on the leg of the 7805 regulator. If I put it in this other position here and test again, and we should get the 5.6 volts. And there you go. So that's the advantage of the external power supply. I'll put it back on 5 because that's what my chip needs. And we'll go and have a look up here at the VPP test point, which is just here. Oh, sorry, we're in the way of the meter. Okay, and the voltage we get is 12.6. So although we've only got 5 volts coming out of this regulator, this buck boost thing is pushing us up to the required voltage. Now I'm going to play with these two jumpers here. I'll pull this one off and put it in this position and see what we get on VPP, and you can see that's 15 volts. And then we'll try the next position with them both in the up position as shown on this silk screen here. Okay, so we've got both in the high position, so we should be getting 21, I think. 21 volts, there you go. Okay, and I want this one in this down position, there, and we'll see, we should get 25. So there you have it. You can see this buck boost system is quite happy to put out the correct voltage from this 5 volt regulator. It's boosting up even to the 25 volt one. Now I've got the USB supply from my power pack for my tablet, so it can put out 5 volts at 1.5 amps. So we'll just check the 5 volts again. So we'll put that there, and we'll check down here on the test point for 5 volts. And there we have it. So it's USB is putting out the 5 volts. I'm not going to shift this jumper again because I know it can't get to 5.6 because the USB is too low. The jumpers are back to the 12.5 volt one, so we try here. That's fine. Let's just try the 25 volt to see if the USB will actually do that. That one, I think. And we'll check it again on VPP, and there we have it. So the USB is quite capable of getting the 25 volts for some of the chips that need it. Now I'm going to have a quick look at the actual programming side of this PCB. And first I'm going to go to this rather nice little program here by Dan Brown, I think it was. I'll put his credits and things in the description below. And this is a nice little program that's been written to verify that your parallel port is going. Now the first thing we want to do is go down here, and I'm going to click here to find the parallel port. Unfortunately, I don't think it shows up, but here it is. So it's found LPT1. I've only got one parallel port on this computer, the one that's on the PCIe bus. And you can see here it's found that lower memory address. So it gives a little bit of a description here about just exactly how to use this program. But basically you can go in and click these data buses things off and on, and you can go into your printer port with the voltmeter, or on the cable from the printer port with the voltmeter, and you can watch it switch the data buses pins off and on. You notice that the parallel port has 8 outputs, something that people weren't aware of. These printer ports, parallel ports, were used mainly for printers, but they were actually bidirectional, and that's how it's being used here. So this just allows you to check all of your IOs working correctly. And you can also see over here that it is a strobe there that can strobe the data in, and you can see here that it could be set as output or input. So you see some bidirectionality there. There's also some other flow control outputs and inputs that can be used for variously clocking the goings on from the Williams software. So I'll leave it at that, and we'll get into the actual board. So now let's have a look at what's going on here. We have this chip here, which has the ability to swap the direction of going, say, from an A bus to a B bus, or from a B bus to an A bus. So that's changes the direction of the information flow, it looks like. This one, and this one, serial to parallel bit shift registers. So data's read in serially and clocked along them to give then you can strobe out the parallel. And this guy does just the reverse. It starts off with parallel data and converts it stepwise to a serial output. Down the bottom here, we have a 3-state buffer. It can put high impedances on some outputs and low on the others, and vice versa. And up the top here, we have a Schmitt trigger that presumably can tidy up if you've got a vague 5 volts to basically put out a rail voltage or 0 voltage, I think. That's probably what that's about. So this is actually a state machine. The program, basically, if you like, is in hardware. There's no software or firmware. There's no data clocks, no CPU. So everything coming from is controlled by the Williams software, and the speeds at which data is fed onto the input and output direction of this parallel port is controlled by the Williams. So given that this is set in hardware, the program basically, these dip switches here give you the ability to reorient all these different bit shift registers to the particular chip needs for the one you're programming. So this is an 8-bit data bus on the parallel port, but the address bus on the chip I'm blowing is actually 16 bits. So somehow they're concatenating a couple of bytes to set up the addresses. And the chip also has an 8-bit output data bus. So it's probably a bit easier to get the message back to the 8-bit parallel port and back to the Williams software. So that's about it for the whole PCB. In my opinion, it looks like it's really nicely made. I think China has come of age in making almost anything at world standard quality these days. Not true back in, say, 2012 when most of the blogs were written. China really has upped its game since then. Where it's weak is that there's very little software, or none, coming with these cards. So all the hardware problems, I think, have been fixed. It looks like a company called Savava, I think, upgraded all the problems, got rid of all the problems it had with voltage, power supplies and things like that. And now it's really nicely made. And they seem to have disappeared. And unfortunately, while the boards survive, there is not an up-to-date schematic drawing of it, except the one I've been showing, but that's out of date. Nor is there a nice user manual for the version 12 of the 98D software. The pop-down menu that I have on my particular version has a whole lot of different commands on it that I've been playing around with to try and figure out. So I'll get into that next video. So now let's start with playing around with the Williams programming software. So you can see I've got it set up for the 27512. I've got a chip in the ZIF socket. I've only got some old, previously used NMOS chips, and they're a bit notorious for being hard to program after they've been used. So let's go here for the action. And the first thing to do is do a blank check. So here you can see it's reading the device, and you can see the device is empty. Okay, so I'll go to the buffer, and you can see that it's all full of FFFs. So I'm going to fill the buffer with a file that's full of nulls. Okay, so now it's going to try programming, and we have every single byte in the whole thing, every single bit, is going to try and program every single one of them because of this thing here. So let's go to action and program test RAM and click on it, and away we go. So you can see it's fairly slow. Yeah, really slow. So I'm just going to finish this video here, and we'll come back when it's nearly finished. Okay, here we are. It's nearly finished programming. So far it's taken about 20 minutes to get to this point. And here we are, it's finished. Okay, so let's just try reading it in and see what we get. Okay, so you see it's had some problems. It's just, so it clearly has not put 0, 0 in every byte. Okay, so I think the thing to try now is to go to here and load the binary file again. Okay, and let's just try going and doing a write again. So we'll just try writing it one more time. Okay, I have tried playing with changing the timing there, and it didn't do much. I might play with it more in the future. But you can see here now, it's programming much faster because it only has it's obviously reading and looking at the ones that aren't correct and just only writing them. So it's quite a lot faster. And when it's finished, we'll have another look at it. Okay, here we are with it just finishing. It's doing a verify. Device programmed okay. So that seems to have done the trick. Let's just test it. Let's just read it back into the buffer from the chip. Okay, and we'll zoom down through and have a look. And it seems to be okay. So it's managed on the second try to program nulls into every single bit. So there it is, programming an old, tired, programming every single bit of the whole 512k bits from a 1 back to a 0. So I think that's about all I'm going to do on this video. Looks like the Willem software is a little bit dodgy, but the board's pretty nice. And I've got some dodgy chips, and I seem to have managed to program every single bit on the whole chip. So I think I'll leave it there. Thanks very much for watching. I know it's been a bit long and tedious, and I'll see you in the next video.